so today, on with the quotient rule. What I want to look at today, you guys know the quotient rule. Let's practice it a couple times. And then I want to talk about how pre-writing is very, very important for using the quotient rule. So let's remind ourselves real quick, what is the quotient rule? If I'm taking the derivative with respect to x of u over v, what's the quotient rule? No. It's remember what's our saying? Low d high minus high d low. So what's that going to be? No, v u prime, right? Low d high. So low is v, d high would be u prime. So v u prime minus u v prime over v squared. There you go. Okay, there it is. So let's apply our quotient rule here. Here's y. So what is y prime? Okay, good. Low, right? So low is squared plus 1 times. Everybody agree? Because the derivative of 2e to the x is 2e to the x, right? Minus times 2x. Good. Divided by calculus is done. Okay, now it's a matter of just cleaning this thing up though, right? Okay. So what could we do here? I mean, what are our options? You guys help me out. Okay, we could multiply out the top. We could expand it all out, couldn't we? Okay, and then combine like terms. Bottom, what do we do with the bottom? Leave it alone. Yep, leave it factored. Okay. Anything else on the top? Can you see something? Play chess with this a little bit. There you go. Perfect. Okay. When I say play chess, I mean think a couple moves ahead. What are you going to end up doing anyway? Well, if you distribute the 2e to the x to all these terms, aren't you going to end up factoring it out of every term eventually anyway? Everybody see that? So a really good idea would be to just factor out the 2e to the x right at the beginning on the top, right? So if we do that, what are we going to get? We're going to get 2e to the x times, what are we left with? I've got x squared plus 1 minus 2x. Well, we could just make that x squared minus 2x plus 1, right? Over x squared plus 1 squared. Good. Is there anything, I mean, that's fine. Is there anything else on the top you see that you could maybe do? What about this part? Yeah, we could factor that, couldn't we? That's a perfect square trinomial, isn't it? How's that factor? Yeah, x minus 1 quantity squared. Good, so we could write this as 2e to the x times the quantity x minus 1 squared over the quantity x squared plus 1 squared. You know, really either one of those would be fine. Bottom one, I would say is slightly better for reasons that will become clear fairly soon. We're going to want to be, eventually we're going to, out of necessity, always be factoring the numerators. And you'll see why when we start to apply this stuff. Okay, give me thumbs on that. Okay, even the people that were gone yesterday, is that kind of making sense what we're doing a little bit? Not completely, I'm sure, but we're just applying this rule. Yeah, no, I know you will. I mean, it's a process. Okay, so now let's focus on this. The goal here is to always try to be really smart about these before we just power through it using a rule. Okay, so what rule, and when I say what rule, I mean what formula, right? We talked about the rules for differentiation. Those are just the patterns that we use. We have a bunch of those, right? We have a pattern for sine, for differentiating sine. We have a pattern for differentiating cosine. We have a pattern for differentiating e to the x, pattern for products, pattern for powers. Which pattern fits here? And it's not to say that there aren't more than one that could fit, but we want to pick the easiest one. Thumbs up or down here. Is this a quotient? What do you think? I mean, it is a quotient, but when I say, when I'm asking you in terms of differentiating here, if it's a quotient, what I'm really asking is, do I need the quotient rule? I don't. You're right. How come? Carson, what could I do here? Exactly, right? When I've got a constant in the denominator, I do not need to burden myself with the quotient rule. It would work, right? I mean, think what would happen here. If we just use the quotient rule, we'd get low d high, so 8 times the derivative of the top, which would be 20x cubed, right? Minus high d low. Well, what's d low? 0, right? So why bother with the quotient rule? It's just a lot of trouble for very little benefit. Instead, we're going to rewrite this as 5/8 x to the 4th. And now what rule do we get to use? A really easy one. Power rule. Yeah, so we differentiate. What do we get? Yeah, 5/2. Good, because we take the 4 out front. 4 times 5/8 is 5/2. X to what power? Third. And simplify? Well, it's already simplified, really. I mean, what else could you do? I guess you could write it as a big fraction if you want to, but that's kind of up to you. You could write it as 5x cubed over 2, I guess, but that one was already simplified. The key there was seeing that it's a power rule problem and not a quotient rule problem because the bottom is a constant. Okay. How do we rewrite this one? Do we need quotient rule? No. What are we going to do? Ashley, what are you going to do? Exactly, right? Just pull the 1/6 out front, and you don't even have to do that. You could just leave the 6 on the bottom if you want to, and just recognize that 1/6 is a constant. Okay, so we're rewriting it as 1/6 times the quantity x squared plus 3, and then we're going to differentiate, and what do we get? I mean, if we leave the 1/6 out front, what do we get? Two x, right? 2x plus 0, everybody agree? When I differentiate? Okay, so we should simplify that. What's 1/6 times 2x? Yeah, so I'll just, like x over 3. And again, we really could. Yeah, did I make a mistake? Oh, it's supposed to be you're right. I forgot the x, didn't I? Yep, you're right. Let me go back, fix that. So what should that have been? It should have been 1/6 times 2x plus 3. okay, which we could write if we wanted to as 2x plus 3 over 6. And I would argue that you could have done that right from the beginning. You could have seen that bottom is, 1/6 is a constant, so just leave that 6 on the bottom and differentiate the top. Okay, give me thumbs. Does that all make sense? Okay. The minutia here that we're dealing with, this is calculus. I mean, this is what a lot of it's about. It's not about getting the right answer. It's about getting the right answer efficiently. Because as you start to get further and further into calculus, in this case, the detour wasn't that massive, right? I mean, big deal. If you had used the quotient rule, you would have gotten there pretty quickly. But as you get into more and more dense calculus, taking those detours becomes more and more painful, right? I mean, you want to always be trained to find the efficient way to do it. Okay, what about this one? That looks like quotient rule for sure. Can we avoid it? I bet you can. How could we rewrite this in a way that would be really convenient? Okay, so what constant would I have out front? -3/7. And then look, I've got this x on the bottom, but I could split that fraction, couldn't I, and simplify those? What's 3x over x? What's -2x squared over x? Hey, how about that? Way easier, isn't it? So when I differentiate then, I've got my -3/7 out front. And what's the derivative of 3 minus 2x? -2. So that simplifies to what? Easy. Again, we can avoid, if you just pause a second, a lot of times if you can avoid the quotient rule, we want to. Quotient rule is tedious, and it's people using the quotient rule makes you susceptible to mistakes. It's a common place where people tend to make mistakes is quotient rule, because there's a subtraction sign in there. People mix up terms. Everybody makes stupid mistakes. I do too. Everybody does. Quotient rule is more susceptible to that. How about this one? We've already kind of done one like this. What would this one be? How could I rewrite this again to avoid the quotient rule? Okay, 9/5. X to what power? Not 1/2. -2. There you go. Okay, good. So then y prime is what? Negative what? 18/5 x to the -3. Good. And if I write that as one big fraction, if I put the x on the bottom, I get -18 over 5 x cubed. Give me thumbs. Okay. Okay. Why is that one worse than the other ones we've done? Okay, right. Can't factor out a constant. But if I go back, like to the first example we started with today, we had to power through a quotient rule one, right? This one, we're stuck using quotient rule, aren't we? There's no way to avoid it. But even so, this is a little bit uglier than the other quotient rule derivatives that we've done yesterday and today. How come? What makes this one particularly ugly? There's a product rule embedded within the quotient rule, right? The numerator is a product. So when we do low D high minus high D low, D high is going to involve what rule? Product rule, right? Okay. So let's do this one. So what goes first? E to the x times, and I'm going to open up a big bracket because I know I've got a product rule coming, right? Okay, so what's in my product rule here? 2x sine x. Who remembers? Derivative of sine is regular cosine, yeah. And that whole thing, that's my du, right? Okay, now what? Okay, so minus, now let's do high D low here. What would high D low be? X squared sine x. It's not going to change Aubrey's answer, but then what's D low? E to the x. There you go. Okay, so there's the top. Now what's on the bottom? E to the x squared. Okay. Okay, so what is e to the x squared, by the way? If I do, oh, never mind. We'll just leave it. Yeah. Okay, so now what? Good. Everybody see that? That's a good one. That's a tough one to see, but how many terms are there in the numerator? Show me with your fingers. How many terms are there in the numerator? It looks like a lot, but I'm talking about on a broad sense at the most coarse level on the top, right? Zoomed out, how many terms are there? The answer is 2. How come? You're right. Because what's the yeah, right. Okay, the reason it's not 4 is because you guys were looking at that plus sign, right? But that plus sign is subsumed inside a factor, right? So it doesn't count. It's not really an outside plus or minus sign. It's stuck inside a product, so we can't see that one. We're only looking for the addition and subtraction signs that are not included inside a quantity or a function, right? There's only one of them. It's right here. Make sense? So there's 2 great big terms. Now within that first term, there's a factor that has 2 terms, right? But there's only one minus sign outside of everything else. So we got 2 terms there. Each of those terms has a factor e to the x. So e to the x is a common factor. You see the big structure of this on the top? If you look at it that way, then it's easier to look for common factors. Okay? So we could take an e to the x out of each of the terms. Here they are. There's an e to the x, and there's an e to the x. And so what are we getting here then? Well, we got our e to the x that we factored out of the top. What else is left in the numerator? Two x sine x plus x squared cosine x minus x squared sine x divided by e to the x squared. Any good cancellation there? Yeah, we can cancel n e to the x, a factor of e to the x. And so it doesn't look like it's not the prettiest thing in the world, but not terrible, right? We end up with our derivative looking like this. Y prime equals 2x sine x plus x squared cosine x minus x squared sine x all over e to the x. Okay, not so terrible. Do you see what I mean by, and again, I better take cover here. derivatives are easy because all you're doing is following rules, right? You just, as long as you are careful about following the rules in the correct order, you're going to get the right answer. I need to like just care this during this part of calc. I probably need to have like a shield up here. I can just duck behind if I need to. Okay, so last issue, an application, right? Here's something important that we want to be able to do. Find an equation of the line that's tangent to f of x and parallel to the given line. Okay, that's a good question. So think what that means. We want an equation of a line that's a tangent line of this function, right? There are an infinite number of tangent lines of this function. We want to pick the one or however many there are. We want to find the tangent lines that are tangent to f of x and parallel to the line. How am I going to do that? Find the slope of the line, first of all. Absolutely. Okay, so let's kind of color code this. We'll make our line is blue. So all the line stuff is blue. What would I do to find the slope of that line? What? Say it again. I heard it. Isolate y. And to do that, we could just push the y to the other side, couldn't we? To isolate the y. So that would give us y by itself equals whatever's left on the left side of the equation, which in this, I'm going to make it the right side. I'm going to flip it. 3x plus 1. So the slope of our tangent line would have to be what? 3. Okay. Now we're trying to find all locations where the tangent to the curve is parallel to this line. Parallel lines have equal slopes, right? You guys already got that. So we know that the slope would have to be 3 because the slope of the blue line is 3. How would I find the places where f of x has a tangent line with a slope of 3? That's it, right? If I want to know where f of x has a tangent line with a slope of 3, slope is a derivative issue, isn't it? That's the job of the derivative, is to tell us the slope of the function, right? We input an x value, it outputs a slope. So we're going to calculate f prime. What is f prime of x? 3x squared. Okay, there's our derivative. We want that to be equal to 3. That's how we ask the math gods. Where is the f of x? Where does it have a slope of 3? There's how we pose the question. They give us the answer through calculus, and a little algebra. So we got to work for it a little bit. What are we going to get? Yeah, right? We're going to divide both sides by 3, and we're going to get x squared equals 1. So what does x equal? Plus or minus 1. Yeah, we get 2 answers. X equals, we'll color code this, 1, negative 1. Whoops. Right? Those are the places. Okay. Let me get that right. 3x squared equals 3. Yeah. Make sense? So then if we want to know what the equation of the line is, how would we do that?
Put in x into the original equation.
Okay, good. What are the ingredients of a line? A point and a slope. We already know the slope. The slope is 3, right? We knew that before we even took the derivative. We were trying to find tangent lines with the slope of 3. So we knew that, but we need to know the points. So one point is going to be the location where x is 1, and 1 is the location where x equals negative 1. When x equals 1, that corresponds to, oh my goodness, corresponds to the point x equals 1, y equals 1, right? How come? Well, because f of 1 equals 1. Make sense? Okay, so now we're just going to use point slope. So we get, to find this line, we go y minus 1 equals 3 times the quantity x minus 1. There's our line. If we distribute the 3 and add the 1, what do we get? What's our line? 3x minus 2? Yeah, I buy it. Okay, there's one line. How about over here with the red one? Okay, so now with the red one, this is giving us the point x equals negative 1. What does y equal? Negative 1. And again, that's just because f of negative 1 equals negative 1. And so we get the line y minus negative 1 equals 3 times the quantity x minus negative 1. If I distribute and solve, what do I get that time? Or distribute and simplify. 3x plus 2. Okay, we could check this pretty easily. Let's do that. Let's use Desmos and just make sure we got what we wanted to get here. So f of x equals x cubed. There it is. We've got the line 3x minus y plus 1 equals 0. There's our line. And we want any lines parallel to the blue line that are tangent to the red graph. And we're going to make that graph, we'll kind of match our color, so we'll make that black. Okay. So we said we had the line, what was one of them? It was y equals 3x, was it minus 2? Up there was one. And we had the line y equals 3x plus 2, didn't we? And that was our red one. Okay, make sense? Everybody see that? And if we could put the points of tangency in here. There they are. There's our beautiful picture. Okay, let's add that to our notes for good measure. Okay, give me thumbs. That all make sense? Yeah. Okay, one more, and I'm going to let you guys. Oh, yeah, yeah. I mean, I can't think of one off the top of my head, but yeah, we do stuff like this. We'll definitely have some. Like when we get up to the section where we're doing applications of differential calculus, we'll see tons of stuff like this where we'll do real problems. Usually the ones we're looking for are horizontal tangents for reasons that you'll see pretty soon, but not always. Yeah, I say that a lot, don't I? Okay, one more and we'll call her good. How about this one? So find the line tangent to f of x at x equals 4. Okay, so we need a point and a slope, right? We can find a point right now. What's our point of tangency going to be? is what? Would you say 446? Okay. Yeah, that seems right. Yep. Right, and we get that because if we plug f of 4 is 3 times 4 squared minus the square root of 4, and that gives us 46. Good. Okay, we need a tangent, though, too, don't we? Okay, how are we going to find the slope of the tangent line? For calculating slope, what do we always have to do? Yeah, we have to differentiate. We have to find the derivative. Okay, so what is f prime of x? Derivative of first term is, okay, what about the next one? How am I going to do that? I want to use power rule. Square root. Okay, good. So we're differentiating x to the 1/2. What is the derivative of x to the 1/2? Okay, and we could write that. Good. So and we had a minus sign there. So we're subtracting 1/2 x to the minus 1/2. So that's going to be the same thing as saying 6x minus 1/2 times square root of x, isn't it? Because x to the negative 1/2 is a square root on the bottom. Okay. So f prime of, makes sense. So what value am I plugging into my derivative to find the slope of the tangent? 4. Good. I want the value of the derivative at the location of the point of tangency, which is when x equals 4. So I get 6 times 4 minus 1/2 times the square root of 4, which is 12 minus 1/4, which is what, 47/4? Yeah. Did I make a mistake? What did I do? Oh, yeah, I did, didn't I? That is, you're right. Last time I checked, you are correct. At least as of a little while ago, 6 times 4 was still 24. I don't know if the math gods have changed that, but I'm assuming they haven't. I think we're good. Oops. Okay, so let's see. What's that going to be? 96. So 95 fourths? So now if we build a line from our point and our slope, we get what? You guys tell me. Y minus 46 equals times the quantity x minus 4. Okay, good. I like it. Okay, and then it would just be a matter of just a little simple algebra. So y minus 46. What do I get when I distribute the 95 fourths? Minus 95. Good. Last step. Add 46. Good. And so I get what? 49? There's our tangent line. Good. Oh, where's the x? Sorry. There we go. Forgot my x. X marks the spot after all. Okay, good. All right. Have at it. You may work a little bit.